Hi. Today I'm going to debut a new math game. It's a game that I created myself, and it starts out with a problem that looks really difficult to solve, and it gives you a shortcut. The shortcut becomes the rules of the game, and this really difficult problem becomes easier to solve. And one of the nice things is that prime numbers are involved. So here's the problem. Let's see. Where's my pen? There it is. Okay, I'm back. Let's make a square diagram, and let's label the corners A, B, C, D, going in clockwise direction. So A, B, C, D. And there will be numbers in these corners, A, B, C, D. And these numbers are all related to each other. These arrows will show how these numbers are related to each other. So the difference of A and B, so that will be like A, minus B, absolute value, 1/2, plus absolute value of D minus C, so this part, so 1/2 the difference of this part plus 1/2 the difference of this part equals the diagonal difference, and so that equals the difference of A minus C, absolute value, and it equals the difference of B minus D, absolute value. So that's pretty cool. And so since these diagonals are the same, we'll just make a little circle here, and it's going to be some number. Let's call it X. Why not? And so this number will be the same, right, for AC or DB. And there's also a relationship between AD and BC. And the relationship between AD and BC is that the number AD, the difference of AD, A minus D, absolute value, is equal to the difference of B minus C. Okay, so these sides are the same, and this is the same, and this plus this divided by half is equal to this. So that's the problem. The problem is can you find the numbers that go in A, B, C, and D to make these equations true. So it seems like a really daunting task. It seems like only brute force will solve this equation, but it turns out that you don't need too much brute force. You just need to make some puzzle pieces and put these puzzle pieces together. So let me show you the grand plan here. We are going to make puzzle pieces. I know this may not make sense right now. Why am I talking about puzzle pieces? It will make sense in about 60 seconds. So puzzle pieces, and we're going to turn these puzzle pieces into tilings. They're also called tessellations. And then we're going to put the tilings, we're going to put the tessellations into A, B, C, or D, such that it matches the conditions that are set forth by that equation. And so the tilings are then going to become part of a circuit. Okay, we're going to call this a circuit, and that's the plan. So I'm going to show you how it's done. I'm going to erase this board, and it'll just be 1 second. Okay. Hi, so we are going to solve a system of equations. The system of equations seems very daunting, very intimidating, and I will show you a shortcut. The shortcut's plan is make pieces, puzzle pieces, tile those puzzle pieces into rectangular tiles, and then those rectangular tiles, we're going to arrange those rectangular tiles into a circuit, and that circuit solves the system of equations. So here's the plan. Pieces go to tilings, also called tessellations, which goes to circuits. And our solution is here. So the pieces will be cut from this block of numbers. The first row are the triangular numbers. So triangular numbers means that if those numbers were marbles, let's say, you can arrange the marbles in the shape of a triangle. And under the first row of triangular numbers is the change of the triangular numbers. So under 6 is 3 because 6 changes by 3 from the previous term. And under that row is the change of the change. So under the 3, that's under the 6, is a 1 because 3 changes from a 2 by 1. And we're going to cut these puzzle pieces out of this block. Which puzzle pieces? Puzzle pieces that have been known to humanity since antiquity and to modern people as well. So some of you may have played the game Dominoes, some of you may have played the game Tetris. Those games use the polyomino pieces. Domino uses ones that have 2 boxes, and Tetris uses ones that have 4. So we're going to start cutting out polyominoes from this block. And so crucially, the polyominoes have to add up to a prime number. So here's one already. 3, 6, 3, 1 adds up to 17. Adds up to 13. So we're just gonna put this here, and here is the polyomino. This is an L tetromino because there are 4 boxes, and we're picking this because this adds up to a prime number. 3, 6 is 9, plus 3 is 12, plus 1 is 13. So here are our pieces. And we're going to get more pieces. So here is another polyomino. This one is called a W pentomino because there are 5 pieces, and this guy adds up to 17. So we picked a W pentomino because it's going to help us make a tiling. So let's start making this tiling. Okay, here's our L piece. Here's our W piece. See how they go together? now you only need one more piece to build out that rectangle. And it's going to be a piece that has 3 boxes. So that's called an L-tromino. And it has to be prime. And this is the crucial point. When we make this tiling, the grand total of all the boxes has to be a prime number. So here is an L-tromino piece. This guy also is from the triangular block. It's 1043. It's there, and now we got a tiling. Now circuits are made from these tilings. The circuits that follow this system of equations that I had put on the board earlier, and we're going to, there was A, B, C, and D. The circuit was made out of 4 numbers, 4 tilings. So we're going to need 3 more tilings. And it would be nice if they were prime. It doesn't always happen. Prime numbers are tricky like that. But I'm going to try to only have primes as examples. So so we have 47 here. Is that right? We have 47 here, and now let's grab another puzzle piece. This guy is from the triangular block 2. This is 13 again. This is a W piece, another W piece from the triangular block. This guy is kind of a big number, but it's over here. It's built from 36 and 45, 9, 10, and 1. It's there. So. Go, and we got to build out the rectangle here, and the rectangle here is an L-tromino, and we want this to equal a prime number. We would really like that, and this is 634, which is 13, and when we add 13 to the other pieces, the grand total is 127, which is a prime number, and we're happy about that. So now we're going to build a circuit, and these numbers are going to exchange pieces, and they're going to exchange the L-tromino pieces. So this tessellation will get 634, and this tessellation will get 1043. And the other parts of the tessellation, the W pentominos and the L tetrominos, will stay the same. So let's indicate that. So 3631 just comes down here. The W pentomino also just comes down here. And same thing for this guy. The L tetromino just drops down, and the W pentomino just drops down, and they're going to exchange these L-tromino pieces, right? So 634 will go whoop, over here, 1043 will go whoop, over here. So let's do that. There's 634. There's 10, 4, 3. And now we have a circuit. So what are we going to call this circuit? By the way, we should verify that that it fits the solution of equations, the conditions from before. So the difference between these two numbers and the difference between these two numbers, half of that difference added together has to equal a number over here that is the difference between this part, and this number is also the difference between this part and this part. So let me repeat that. So the difference between let's label these. The difference between A and C is a number which is equal to the difference between B and D. So the difference between these numbers, so this is 127, this is 47, this is 43, and this is 131. The difference between these two numbers is 84. The difference between A and C is 84. The difference between B and D is also 84. So far so good. And now we have to verify that half of A minus B plus half of D minus C is equal to this number in the middle, which it is. So the number in between these is 80, and the number in between these is 88, and the difference is the average is 84. So and now we have to verify that the numbers over here are the same, because that was also part of our conditions, that BC is the same as AD, and the difference between 47 and 43 is 4. The difference between A and D is also 4. So that completes the circuit. So we're going to call this circuit 84, actually, because we have a group of numbers here. They have a symmetry. We got to give them a name. And since they have 84 in common, we're going to call it 64. We're going to call it 84, circuit 84. So so this is a shortcut that uses puzzle pieces and prime numbers, and it's a combinatorial. It's like uses geometry and combinatorial geometry to solve like a really difficult system of equations. So let's do another example, and thank you for watching this so far. Great. So we just did an example of creating puzzle pieces from a block of numbers and making those pieces into tilings, and then those tilings, we get 4 tilings, and we kind of put them into this, circuit, and the circuit is like a diagram representation of a solution of a system of equations. So the diagonals of the circuit and the sides of the circuit, they're all related to each other. We did an example. We're going to do another example. So let's take a prime polyomino like we did before. And here is 3, 6, 3, 1, which comes from this block. Thank you for your patience as I deal with the Scotch tape. I'm trying to give this video a real homemade feel to it. So that is so now that's an L tetromino. We want to turn this into a rectangle, so we need a piece that looks like a W and a piece that looks like a little L for the final corner of the rectangle. So let's get that piece. So here is another W piece, 10, 15, 5, 6. This polyomino is prime. It adds up to a prime number. We need a final L terminal piece. So then we add 7 to the total so far, we get a prime tiling. So that's good, because I think that prime numbers, at least having 3 or 4 prime numbers, makes it easier to solve that solution of equations for some reason. I only have solutions for this equation that uses 3 or 4 prime numbers. So so this number is 47. Let's get another prime. Here is an L tetromino. Here's a W pentomino. Now, of course, this triangle, this L terminal piece, the final piece that completes the tessellation, will be different from this piece, because these pieces are going to switch places to make the two final tessellations, which will give us the circuit, hopefully. So the L terminal piece there is 634, and that number is 43. So now, since only the L terminal pieces are getting exchanged, the W pentomino and L tetromino pieces just move down. So this is A, this is B, this will be C, this will be D. So this just moves down. This moves down. This moves down. And now this will go over here, this will go over here. Again, thank you for your patience during the arts and crafts hour here. I do think this is artistic, by the way. I definitely think this has some aesthetic appeal to it. Tilings always have been associated with beauty. So this is 2. Okay, so this 7 goes over here. So the numbers that we have now are 53, and 37. Let's check if they match the circuits, if they fulfill the solution of equations, system of equations. The difference between 43 and 53 is 10. We want the difference between B and D to also be 10. The difference between 47 and 37 is 10. So far so good. We want the length of B and C to be the same as the length of A and D. The difference between 47 and 53 is 6. The difference between A and D is 6. That's good. Now, we want half the difference of this added to half the difference of this to be equal to 10. So this is 4, and this is 16. 2 plus 8 is 10. So that matches. So we have found another circuit using this combinatorial geometric shortcut that makes heavy use of primes. This circuit is let's call this circuit 10. So that's called circuit 10. And now we're going to do something neat. We're going to combine the circuits together. Why not, right? Let's join circuits on where the tilings are the same. So let's do that now. So these are the circuits that we have built, joined together where the tessellations are the same. So circuit 84 has the same tessellation, tessellation 43 as circuit 10. So we join circuit 10 and circuit 84 on 43. Note there are two different types of 47. There are two different tessellations, but 43 was identical in both circuits, so that's where we joined the circuits. And we got a super circuit. So I think it's really interesting to see this level of increasing complexity. We started from puzzle pieces. We built the puzzle pieces into tessellations, and then we grouped the tessellations into circuits which solve a system of equations that really felt impossible to solve without using this really cool geometry-based shortcut that made a heavy use of prime numbers. So about the prime numbers that are featured in this super circuit, you can say some interesting things. For example, 47 and 53, they have a difference of 6, just like 43 and 37 have a difference of 6. And mathematicians call these sexy prime numbers, after the Latin word for 6 is sex. And we usually use Greek prefixes like hex, but it's a pun because mathematicians really love primes, right? They're really appealing. So instead of calling these hexy primes, mathematicians call them sexy primes. Fair enough. These numbers, 127 and 131, have a difference of 4. 47 and 43 has a difference of 4. These are called cousin primes, primes with a difference of 4. Why are they called cousin primes? Because they're next to twin primes. Twin primes are primes that have a difference of 2. So that was kind of a genealogical motif. Another thing we could say about the primes featured in these in the super circuit, all of them, so 131, 127, 47, 43, 37, 47, 53, they're all Higgs primes. And another cool little tidbit is 43, 47, and 53 are consecutive primes. They are right next to each other. So I submitted this to American Mathematician Monthly because I'm really proud of this discovery, and I think it's a great basis for a math game that could get people really interested in numbers, as well as foster teamwork and reasoning skills, and people can compete because there could be competition for bigger and bigger, super circuits. I only joined 2. Maybe there's a way to join 3. So I really will thank you so much for staying with me during this long video. I would love to hear what you think, and yeah, so just comment below. Thank you very much. Hey, just one more thing I forgot to say. This is mathematically consistent as well. So this was circuit 84, and this was circuit 10. And when we joined them, we connected their corners in a mathematically consistent way. The corners were diagonal, because 127 minus 84 plus 10 equals 53. So it's really cool that it works out that way. Also, the 634 gets exchanged on the diagonal. So the 634 gets exchanged here. The L terminal piece, 634, gets exchanged here, and this receives the L terminal piece. So this is a really interesting thing to see, how it kind of all fits together. So thank you again, and please tell me what you think below. Thank you so much.